Today's topic of discussion is example number 8.7. Okay, express the constant k of equation in days and kilometers. Here k is given. The value of k is 10 to the power minus 13 second square meter raised to minus 3. Now this constant is appearing in this equation that is already discussed by us. Okay, t square is equal to kr cube, or we can say square of the periodic time of revolution of any planet is directly proportional to the cube of its semi-major axis or cube of the radius of the path, we can say, and that is expressed here. Okay, t square is equal to kr cube. Now value of k is known to us, and that is to be expressed in terms of days and kilometers. Okay, now see, first of all we want to convert the second into days. Now 1 second is converted into days. As you know, there are 24 hours in a day, and there are 3600 seconds in 1 hour. So if you want to convert 1 second into day, then 1 second divided by 24 hours, and 1 hour is having 3600 seconds. So this is the conversion of second into days. And 1 meter is nothing but 1 kilometer. As you know, 1 kilometer is equal to 10 raised to 3, that is 1000 meter. So we can say 1 meter is equal to 1 upon 10 to the power 3 kilometer. So this is the conversion of meter into kilometer. Now the value of k is given. Okay, the value of k is 10 to the power minus 13. Now second square, so this has to be squared. So this has been taken as square. Now meter cube is in the denominator, so this has to be taken in the denominator, and then we have to take the cube of it. So it is put here, or it is taken in the denominator, 1 upon 10 raised to 3, and the cube is taken. Now just we want to simplify this. Okay, by using the calculator you can easily solve this. Okay, and we can say that this answer of k in 10 to the power minus 13, that is in the second square per meter cube, that is converted into this particular number, that is 1.339 into 10 to the power minus 14 day square per kilometer cube. Now the next part is given. The moon is at a distance 3.84 into 10 to the power 5 kilometer from the earth. Obtain its time period of revolution in days. Okay, now we want to find the time period of revolution of the moon. Okay, so we know this is the formula, that is t square is proportional to r cube. So t square is equal to k r cube. Okay, values are written. K we got in days. Okay, this value. Then r is the distance, which is given 3.84 10 to the power 5 and cube of it. Okay, so that is done. And if you simplify, then you will have this, that is 758.18. okay, and if you take the square root of it, okay, because this is the square, and you take the square root, you will get approximately about 27.5 days. Okay, now we are having the next illustration, example 8.8. okay, 400 kg satellite is in the circular orbit of radius 2re. Okay, radius of the orbit initially is 2 times re. Okay, about the earth. Okay, how much energy is required to transfer it to the circular orbit of 4RE, what are the changes in the kinetic and potential energy? Okay. Now see, as you know that the energy associated with any revolving satellite is given by, initial energy is given by, in general, this is a general formula, minus G MEM upon R, where Me is the mass of Earth around which the satellite is revolving, okay, and small m is the mass of the satellite. Here R is the distance. Now initially the distance is how much? It is 2RE, okay, rather it is rather 2RE, 2R rather, the equation number 8.42 which we have derived, okay, in the theory on page number 196, there you can refer this, okay. The energy is generally given by minus G MEM upon, as such it is 2RE plus H. Now if you take this RE plus H as small r, okay, then the equation will become minus G MEM upon 2R, okay. So the equation which is derived by us already, that is on page number 196, that you have to refer, okay, that is energy of satellite which we have derived, okay. So in general the energy of satellite is given by, initial energy of satellite we can say EI, then it is minus G MEM upon 2 times the distance. Now this distance initially is taken as 2RE, so this energy will become minus G MEM upon 4 times RE, that is written here. Now when you take this satellite at a distance 4RE, and instead of this small r we write 4RE, so the equation will become minus GMEM upon 8RE. So these are the initial and final energies. Now just we have to take the difference, final energy minus initial energy, and we just have to simplify this. Now on simplifying, it is very easy, okay. Final energy minus initial energy, it has been done, okay. So we can have GMEM upon RE as common, and if you simplify, then finally the difference of energy will be GMEM upon 8RE, okay. Now just we are multiplying this equation by RE, okay. Just we are multiplying so that it can be easily calculated. We multiply by RE and divide by RE, so we will have GME upon RE square, and that is nothing but small g, okay. So we are having this GME upon RE square, okay, GME upon RE square into M, okay, into this M is extra, this is misprint, okay, GME upon RE square into M into RE upon 8, okay. So this part will become small g, okay. So small g M RE upon 8, all the values are known to you, just simplify, okay, and you will get delta E, that is change in potential energy will be, rather change in energy will be 3.124 into 10 raised to 9. Now reduce in kinetic energy is denoted by delta K, so we can say that the reduction in the kinetic energy is done, okay. There is change in potential energy, okay. So there will be a reduction in kinetic energy, that is minus 3.124 into 10 raised to 9. So change in potential energy of the satellite Okay, that is delta U is equal to minus 2 times delta E. Okay, and that is nothing but minus 2 into 3.124 or 125. Okay, approximately it will be minus 6.25 into 10 to the power 9 joule. Okay, thank you. Here we complete the illustrations. Next time we shall discuss the numericals. Okay.